So here we're going to look at a two-sample hypotheses test when the population standard deviation sigma 1 and sigma 2 are not both known. So not both known means that you don't know either of them, or it could mean you know one of them and not the other, because when you know one and not the other, it still means they're not both known. So long as they're not both known, you're going to get a t-distribution, and we're going to have a look at it right here. You can see that everything looks very similar to when we had the normal distribution. This looks the same. The test statistic looks very similar. It's not exactly the same. Instead of having sigmas in here, because we don't know them now, we put S's, the sample standard deviations. Everything is fairly similar. I mean, we could flesh it out right here. So we can actually say, look, for this particular one here, this time it's going to be a t-distribution rather than a z-distribution, but it's still going to be a two-tailed test. This combination of equals not equals leads to a two-tailed test. So we have two critical values, one here and one here. And the do not reject region is going to be right here in the middle. So do not reject H0. Do not reject H0 is going to be right here. And then we're going to get reject H0 here, reject H0 along the edge here, and reject H0 along here as well. And the critical values are going to be t critical values. On this side it's going to be a positive 1, and this one to the left of 0 is going to be negative, so this one's going to be minus t. And this is a two-tailed test, it's going to be t of alpha over 2 with a certain amount of degrees of freedom. And we're going to have to use the template to work those out, and like I tell you below here, that degrees of freedom, use the Excel template as we did in the previous example. And it's going to be plus t of alpha over 2 with however many degrees of freedom it comes to. Okay, so that's that one. And then how about the next one? The next one down here. Kind of went a bit overboard with the space. The next one down is going to be a one-tailed test with a rejection to the right-hand side. Still going to be a t-distribution, they all are. Rejection is to the right-hand side, and the critical value is going to be plus t of alpha, not alpha over 2, or however many degrees of freedom. And the rejection, as we said, is to the right, so the reject is going to be along here. It's going to reject H0 region, and the do not reject H0 region is going to be over here. Do not reject H0. And hopefully you're beginning to see patterns in this stuff. Even if you're not, I recommend that you have something like this on your cheat sheet. And this final one here, it's going to be a one-tailed test, rejection to the left. Still t-distribution, 0. Rejection is going to be to the left, so your critical value is going to be on the left as well. And we're going to get reject H0 along here. And we're going to get our do not reject H0 down here. And the critical value is going to be, because it's to the left of 0, it's going to be a negative, and it's going to be t of alpha, not alpha over 2 because it's only one tail, and we'll have to put the degrees of freedom, df, in there. And this looks very similar to what we did before as well. As I said, the only difference is that we had, instead of having population standard deviation, we have sample standard deviation. So let's actually look at an example. It's a follow-on example from the one we did before. We're still looking at the American and Japanese cars comparison, and we're comparing the actual miles per gallon. So it's the same data, and now it says, can we conclude using a 5% level of significance, so that means alpha is 5%, that the miles per gallon performance of American cars, or M cars, is greater than the miles per gallon of Japanese cars? So to do that, we're going to start off by saying, well, let's look. Let's suppose the average mile of American cars is mu1, and the average miles per gallon of Japanese cars is mu2. We want to find if American cars, the average mileage of American cars is greater than that of Japanese cars. What we need to do, it's not an absolute necessity, but it's the way that the convention goes. We need to express these as a difference. So as a difference means I have to say mu1 minus mu2. Well, to get to mu1 minus mu2, I subtract mu2 from both sides. So this side is going to end up with no mu2, it's just 0. So if I subtract mu2 here and subtract mu2 here, I end up with this. Now I'm going to look back to see, do I have a scenario, one of those three scenarios, or those three conventions where I have that? So let's look back. And yes, I do. It's right there. So basically, I've got this entire scenario to pick up. This is going to be a one-tailed test, rejection to the right. The null hypothesis is going to be this one in here. So let's just go through and add those in. So we're going to have our alternative hypothesis is this guy in here. The null hypothesis that will go with that will be H0. That's going to be mu1 minus mu2 is less than or equal to 0. Does it have to be 0? No. What is that figure on the previous page? What is this D0 over here? That's just any number. It could be 0, it could be anything. In our case, D0 is going to be 0. It could be anything. Typically it's 0, but it doesn't have to be. So this is going to lead to, as we said, a one-tailed test with rejection out to the right-hand side. So, and because we don't know we only know the sample standard deviations, we don't know the population standard deviations, it's going to be a t-test, t-distribution. And there you go. Our test statistic is actually going to be t of alpha with a certain amount of degrees of freedom, however it's going to be. We actually know what the degrees of freedom are because we actually did it for the previous question using the Excel template, and it happened to be 40. So our rejection zone is going to be over here, and our do not reject zone is going to be on the other side. Now this is supposed to be all our data, so there's an underlying assumption that our data belongs to a bell curve. You don't have to put it in. I will put it in right now for a point I'm going to make in a few moments. So we need to find our critical value here and our test statistics. So we could start off by finding our critical value. Our critical value, well, alpha is 5%, so it's going to be t of 5%, and the degrees of freedom are going to be 40. We know that from the previous question. If you put the data into the template, if you forgot that what we did, put this data into the Excel template, and you'll be able to actually find the degrees of freedom as being 40. How do I actually work this out? What do I need to put into t dot inverse to work this out? Because the t dot inverse is going to ask me for a probability, and the probability is going to ask me for, what is it going to be? Well, the rejection zone is what alpha is, and that's 5%. Excel wants to know the area to the left of your critical value, and the area, if the area to the right is 5%, then the area to the left is 95%. So this is going to be 0.95. The other thing Excel is going to ask you for is the degrees of freedom, and the degrees of freedom are 40, worked out on the template from before. Just look at the previous video, and that's going to be 1.68. Could I have a quick look at Excel? So if we use Excel, this is all we need to do. You can see that says t dot inverse 0.95 and 40, and once you put that into Excel, you're going to get 1.68, 1.684, and let's just go back to here. So this value in here is going to, well, this is going to be equal to 1.684, and that's our critical value. And then, which is this value in here. And then, shall I put it in there? Yes, put it in there. 1.684. And then once we work out the test statistic, if the test statistic falls to the right of this, then our conclusion is reject. And if it falls to the left, it's do not reject. So we need to find out our test statistic. And our test statistic comes from this formula in here. There you go. So now we have to work out this formula in here. So it's very similar to what we did before, but we can just look at it one more time if you want to get a little bit of extra practice. So it's going to be x1 bar minus x2 bar, the top part, the numerator. So the test statistic, I like to call it the standardized test statistic, but it's still the test statistic, is going to be x1 bar minus x2 bar minus d0. That's going to be divided by the square root. Do you remember what it was? Was it sigma 1 squared over n1 plus sigma 2 squared over n2? Let's have a look. Sigma 1 squared over n1 plus sigma 2 squared over n2. So let's go back down and put that in. So it's going to be, I'm sorry, it's not sigma, it's s, isn't it? s1 squared over n1 plus s2 squared over n2. And we've pretty much got all that data. x1 bar, we've got all the information above. x1 bar is the sample, so sample size is going to be n, and this is going to be the mean, x bar, and this will be the standard deviation. So n1, n2, x1 bar, x2 bar, s1, s2. So to put that data in, when we put that in, it's going to be x1 bar is going to be 29.8. Just check, make sure that's right. 29.8 minus 27.3. So 29.8 minus 27.3. Okay, minus d0. d0 is just whatever number is to the right of your null hypothesis. It's the difference, d's difference, it's the difference of your null hypothesis, and it happens to be 0. And then we divide that out by the square root of s1 squared, and it's s1, it was 2.56, I believe. Yep, you see it there, s1 squared, s2 squared is 1.81. So it's going to be 2.56 squared, 2.56 squared divided by sample size, which was 24, plus 1.81 squared divided by 28. Now we did something very similar to this in the previous example. So I'm just going to put a result of what that comes to. Approximately comes to 4.00 or something like that, 4.0. But whatever it's coming to, let's have a look. Where's it for? 4.0 is going to fall way out here. So our conclusion is reject H0. So again, on this question, we reject H0. Now, even though they didn't ask us about H0, this is the initial statement they gave us. I still ran the test on H0, and I get a result for H1, because after I've got a result for H0, the result for H1 or HA, the alternative hypothesis, is going to be the opposite. So if this is incorrect, this is correct. So that's saying it does appear that the average mileage for the Japanese cars is, for the American cars, mu1 was the American cars. The average mileage for the American cars is indeed greater than the average mileage for the Japanese cars, based on the information we have before us. Do you remember what that approach was called that we just used, where we used the critical value? That was called the critical value approach. So now we're going to just look at the p-value approach, and for the p-value approach, what we need to do is we say, look, well, we've got our t-distribution, and this is 0, and we need our test statistic, and our test statistic is around 4, and that's our test statistic, 4, that value in there, so put it down to here, and we need to work out the area in this tail here, and to work out that area in that tail there, it's going to be 1 minus t dot dist you can put a more accurate figure than 4. The degrees of freedom are 40. The template worked that out for us. And then 1 or true. And when you do that, you're going to get a value coming to approximately equal to 0. And what does that mean? Well, we remember that when alpha is greater than or equal to the p-value, our conclusion is reject H0. Now for us right now, what was alpha? Let's just remind ourselves, alpha for this question was 5%. So 5% is indeed greater than or equal to 0%. Remember the p-value was 0 up here. That was the p-value, was 0. So that implies that we reject H0. So we've just solved the problem twice. Once using the critical value approach, the first approach, and that concluded reject H0. Then we did it again using the p-value approach, and that again gave us the same result. Using the p-value or the critical value approach will always give you the same solution unless you've made a mistake.